Okay, in this video we're going to look at another optimization problem, and you can read it right here. And basically the key to this problem is drawing a very accurate picture. So what I'm going to do is I'm going to pretend that ship B starts from the origin and is going to sail due south, and ship B is going to start 100 kilometers away from the origin. Okay, so at any given moment in time, we should be able to figure out where this guy actually is. This is ship A right here. We'll say ship A. And initially, remember that he starts off at 100 kilometers away from the origin. Ship B, though, we'll put down here. And remember, he initially started off right here. This will be ship B. Okay, so in the very beginning, when ship B is here and ship A maybe is way out here, they're 100 kilometers apart. But then ship A starts sailing to the origin, ship B starts sailing down away from the origin. So really the distance that we're interested in minimizing is this guy right here. Okay, and you can see that this actually makes a nice little right triangle. Okay, right here, here's our right triangle. Well, let's try to describe this ship as an ordered pair at any given moment in time. Well, if we let time equal to 0. This is time equals 0 corresponds to noon, let's say. I guess it doesn't have to be noon. This is kind of arbitrary right here, but time equals 0 corresponds to noon. Well, at 1 p.m., 1 hour goes by. How far did ship A sail? Well, it's going 12 kilometers per hour. So if it started off way out here at 100 kilometers away from the origin, 1 hour goes by, it's going to sail 12 miles closer. 2 hours that goes by, it's going to sail another 12 kilometers closer. So really, you can describe this ordered pair as 100 minus the rate that boat A is traveling multiplied by the time. Understand, this is just a distance. For every hour that goes by, you're subtracting 12 more kilometers. Okay, well over here, I guess I should, oops, let me change something here. This should be comma 0. This is an ordered pair. Now over here, I want to describe this ordered pair. What's this ordered pair? Well, the x-coordinate is going to be 0. Okay, and how far down did we come? Well, every hour that goes by, I'm going down 10 kilometers. I'm going south 10 kilometers. Okay, so now we have a way to describe each side length of this right triangle in terms of t. And if we consider this guy d, then we can write a nice little equation using Pythagorean theorem. So let's go ahead and do that. We have d squared equals, what would it equal? Well, what's the length of this guy? It's going to be this x-coordinate right here, and it's going to be 100 minus 12t squared. All I'm doing is Pythagorean theorem here, plus the other side length, this side length squared. Well, what's that? That's the y-coordinate of this point. So this is negative 10 squared. Okay, so if we simplify this, and I'm going to skip some steps here, I'm going to assume you can do some expanding here, and if you expand it and combine some like terms, you get the following. You get 10,000. 10,000 minus 2400t plus 244t squared. 244t squared. Okay, there you have it. Now, I'm going to do a little trick here, and I'm going to call this d squared. I'm going to call it L instead. I'm going to really say L is equal to d squared. Now, I want you to think about this. If we're going to minimize this distance, then really, if I minimize the distance, then really d squared will be minimized as well and we don't have to take the square root of both sides to get a messy derivative. So really, if I minimize d squared, then effectively that's going to minimize d as well, and that's d squared will be minimized for a certain value of t. So I'm just making the substitution of L. That way I can differentiate. That's not what I wanted to do. I want to differentiate. Let me put some brackets around here. This entire thing with respect to t. Okay, so we're making the substitution of L in for d squared, so we really have L equals all of this. Okay, so what's the derivative of L with respect to t? Well, it's just dl dt. The derivative of 10,000 is 0. The derivative of negative 2400 t is negative 2400. And the derivative of this is going to be positive 488 t. Okay, so now we set that derivative equal to 0 and we solve for t. And if we do this, we get 0 equals negative 2400 plus 488t. And if we solve this, we get t is equal to 300 over 61, I think is what you get. 300 over 61. Now that doesn't make a whole lot of sense in terms of hours until you plug it into a calculator, and you should get 4.92 hours. Okay, now if you do some reasoning here real quick to make sure that this really does minimize it, you could think of it a couple of ways. If you were to, I don't know if you can see that or not, let me just get back up here a little bit. If you were to graph this thing, remember this is really L equals this quadratic equation in terms of t. Well, if you were to graph that thing, then this is going to be a parabola that opens upward. So you could kind of think of it this way. I have no idea where this thing actually lives, but this is going to live something, it's going to do something like that. And this is the value that we just found most likely. We probably just found this guy right here where there's a horizontal tangent line there. So you can kind of reason that way. Now the other real quick way to do this is just to take the second derivative of this, and by doing that you would have the following. You'd have d, the second derivative of L with respect to t is equal to, what would it be, 488. Well, what does that mean? That means your second derivative is positive everywhere. And if your second derivative is positive everywhere, if it's positive, that means you're concave up. And if you're concave up, then at 4.92, this thing definitely is a minimum. Okay, so this thing right here truly does, there we go, truly is a minimum. Okay, the only thing left to do is to figure out what exactly is the distance at 4.92 hours. And to do that, all I'm going to do is I'm going to substitute t back into this equation right here, and I'm going to solve for d this time. I'm not going to solve for L, but I'm actually going to solve for d. So plug in 4.92 in for t right here, and if you do that, I'll show the substitution. I just won't take the time to actually calculate it. I've already done that. You get 10,000 minus 2,400 times your t plus 244 t squared. And if you make this substitution really quick, you're going to substitute 4.92 in for t. This is sloppy, I know. There you go. If you do that and solve for d, take the square root of both sides, you should come out with 4,098.36 kilometers. Okay? So there you go. We've optimized it. These ships are the closest at just under 5 hours, and they are a little over 4,000 kilometers apart. Hope that made sense. We'll see you around.